Okay, so we want to approximate data that looks like this, binary data or potentially probability data, um, using a function that looks like this, that captures the transition as well as the steepness of the transition from probability 0 to probability 1. Okay, and that's what we call logistic regression. We want to find, in this case, b0 and b1, these two coefficients in this very simple problem, right? So this is a one input, one output problem. We will generalize this in the next few videos very quickly to make it very general. But in this particular very simple case, we want to find two real numbers, b0 and b1, such that the resulting sigmoid best approximates either binary data that looks like this or potentially data that already looks like a probability. Okay. Okay. How do we do that? So for this, let's just use some standard notation. Let's say the input is x. Instead of saying sigma, which we motivated using stress, let's say the input is x, which is a real number, and the output could be 0 or 1, so binary, or it could be a probability that ranges anywhere between 0 and 1. The following will apply essentially to both those conditions. And I'll sort of make appropriate remarks at the relevant places to distinguish between the two possibilities, whether you have a binary data or whether you have sort of continuous probability data. Okay. Okay. So just to define some functions, we call the standard sigmoid g 1 over 1 plus e power minus z, and then this transformed sigmoid h of x, where it's 1 over 1 plus e power minus open brackets b0 plus b1x close brackets. Okay. So what do we want to do? So this is what is this function trying to do? This function is basically trying to predict the probability of failure, for instance, in this particular situation. Or more generally, it's trying to predict the probability that the output is going to be 0 versus 1. Okay, or if you do a lot of trials at a particular x value, this is expressing the fraction of outputs that will be 1 versus 0, right? So what this h of s is trying to do is basically trying to approximate this probability. So what we might want to do is basically say this h of x is as close to this probability data as possible. If it's probability, it turns out the same thing works if you have binary data as well. You want really this prediction to predict whether it's going to be a 0 or a 1, right? So what you can do is basically say we want to minimize the difference between this predicted probability, whether it's 0 or 1 or whether it's between 0 and 1 included, and the actual value of y, whether it's again 0 or 1 or whether it's continuous probabilities between 0 and 1. Okay. So we might try to minimize the mean squared error, just like we have done before, between this weird function. Previously, we were trying to minimize the mean squared error between y and just a linear function or polynomial functions and so on. Now we have a more complicated function that involves exponentials and divisions and things like that, right? So it's a somewhat nonlinear function. Okay, so we could try to minimize the mean squared error. It turns out that minimizing this mean squared error is not a good idea because it results in a minimization problem which can be non-convex in these coefficients. In other words, if you plot the mean squared error with respect to b0 and b1, it can look like this depending on the data and depending on the situation, at least in this general case. And it turns out that if you have lots of little bumps like this, it may be hard to find the global minimum. In other words, the values of b0 and b1 that minimizes the mean squared error the most. Okay, it may be hard to find analytically or even numerically. So rather than minimize this mean squared error, we minimize a different function, which is called a logistic loss function or a log loss function. There's a few names for this function which I'll talk about in a later lecture. Well, it's right here, in fact. Another name for it is called the cross entropy loss function. We can talk about why this function is called these other things. So I haven't quite described what the function is. Let me just describe it. Okay. So what this function is trying to do is trying to find some kind of difference between the actual output y in the data and the predicted output h of xi. Okay. Really, we want to find the difference between the actual output and the predicted output and make it as small as possible so that our predictions are really good, right? And this logistic loss function is a different way of doing that. What is the difference between prediction and the actual data, or how good is my prediction compared to the data, right? So there's a different way of formalizing that or encapsulating that quantity or that idea, I guess. Okay, so this is what the logistic loss function looks like. Imagine you have n data points, y1, y2, y3, etc., are the outputs of those n data points. If yi equals 1, we say the loss function contribution from the data point is minus log h of xi, and then if the actual output in the data set is 0, then the loss function, the logistic loss function value for the data point is minus log 1 minus h of xi. Okay, it's very weird if you just look at it for the first time. And then once you assign these values for each data point, you sum over all data points to get the total logistic loss function. Okay, instead of mean square error, we have this thing called the logistic loss function. I'll talk about this terminology loss function in a separate video, but the word loss function just means, at least in our context, some measure of performance that we are trying to minimize, okay, or some measure of fit that we are trying to minimize. How in this case bad the fit is. That we are trying to minimize that badness. Okay. Okay, so this is how the logistic loss function is defined. Summation over all data points of Li, where Li is defined as this quantity if the data point has y equals 1, and this quantity if the data point has y equals 0. This is if you have binary data, and then if yi is more like probability, continuous probability data that can take values between 0 and 1 as well, then you write this in this more general form, okay, where for each data point you have this expression. Okay, notice that this expression, just to be clear, is dependent on both the data point, both the actual given data, which is yi, and your prediction of the data, which is h of xi, right? This expression is literally a difference between your prediction and the actual data, squared and averaged. Here, it is some function of the data yi and your prediction h of xi, which I'm claiming also measures some kind of difference between your prediction and the data. It's unclear immediately how it does that. But suffice it to say that it's basically finding some kind of a difference between your prediction and your data. Okay, we'll provide some intuition for why it's a good idea to do this, or at least why it's a reasonable idea to do this in the next little video.